Good evening, everyone. Thank you all for coming. What a great group. Firstly, we would like to acknowledge that we're meeting on the land of the Kulin Nations and pay our respects to their elders past and present. And welcome to the monthly Beyond Zero Emissions discussion group. My name's Hugh Venables and I work in a workshop at Monash University, and I've been a little bit involved with BZE for a few years, and I'm a volunteer presenter, which means I present at this stage the stationary energy report, which is part of the Zero Carbon Australia plan, to interested groups, and there are quite a group of us that go around and do this from time to time. We'd like to thank the University of Melbourne Energy Research Institute, our Zero Carbon Australia project partners, for this great venue. For those of you who haven't been to one of our discussion groups before, BZE is a climate change solutions think tank and research organisation and communication. Our goal is to transform Australia from 19th century fossil fuel based economy into a 21st century renewable powered clean tech economy. Our projects include the Zero Carbon Australia research, Repower Australia talks, media work, education programs and more. This discussion group is a forum for climate change solutions with presentations by experts in their field, and is held on the first Monday of every month. This month we are very pleased to have Dr. Scott Watkins, the stream leader for organic photovoltaics in the Materials Science and Engineering Department at CSIRO, who is developing next generation organic solar cells. He will talk about the new manufacturing facility in Melbourne printing solar cells at the size of an A3 sheet of paper, which are one of the largest in the world. The Victorian Organic Solar Cell Consortium, VICOSC, has developed processes that use spray coating, reverse gravure and slot die coating, as well as screen printing. And the technology that has gone from producing solar cells the size of a fingernail to 10 centimetres square in 3 years. Dr. Watkins says the new $200,000 printer has allowed the VICOSC team to jump to producing solar cells on sheets 30 centimetres wide, right here in Melbourne. The flexible organic PV cells have applications in consumer devices and small integrated electronics, and into the future they could be coated onto buildings, into windows and onto roofs. Dr. Watkins will now explain to us organic PV technology and how the printing process works. Please welcome Scott Watkins.
Thank you. Thanks everyone for coming along today. I'm really honoured that you've taken the time to come along tonight and hear what we're doing. I'm very aware that a lot of you know a lot more about renewable energy than I do, and so if I can add to that knowledge tonight, that'd be great. So I'm Scott. I represent the group at CSIRO who's doing this work on specifically printed solar cells, but more broadly this area of flexible electronics. And as was introduced, we work very closely with research partners here in Melbourne, particularly the University of Melbourne here and Monash University. And we've been developing this for the last few years, and it's something that we're really excited about. We've still got some way to go, but I want to tell you the story about what we've been doing so far. So what I'm going to go through tonight is just a few aspects of the technology and flexible electronics in general, and give you the state of where we are with the different aspects of it, particularly with the printing. And I want to finish just with a couple of comments about where the technology fits and some aspects of science communication as well. So I'm sure, hopefully all of you are aware that CSIRO is your taxpayer investment in research and development for Australia. We're a pretty big organisation now, about 6,500 people across the country, and our site here in Melbourne is mainly the site of our materials research. But we have obviously the sites all around the country, and I think one of the big changes in CSRO in the last few years has been this move to our flagship project, where we've got large-scale projects that draw on expertise from across the organisation in these different domains that are addressing specific big-picture problems for Australia. And just as a reminder or an introduction about some of the things that CSRO has developed over the last few years, and these include the polymer banknotes that we're all carrying around, and things like the lens of fluid treatment, And what's really, I guess, the significant part about this story and what I'll go on to is the work that CSRO did in developing the polymer banknotes and the capability that we built up in the organisation and with our partners has now sort of come around and is contributing to other areas. So I'll come back to that part of the story as we go on through this evening. The way that we work with different parts of the economy in the country is by partnering or doing research to help them grow new aspects of their businesses. We also work with a number of large multinational companies to enable us to validate the approaches we're doing and grow new areas of manufacturing, particularly, and grow different areas of industry in Australia. The path to impact or path to market for our technologies is varied. We either license it through companies, had success in creating spin-out companies, or selling that IP on and then reinvesting that in research back in Australia. The proceeds from the wireless, the Wi-Fi patents is probably one example of where a large amount of money has come back to Australia, and that's now been reinvested across the whole innovation system, not just in CSIRO, but there's money from that being invested in all aspects of university and research in general across the country. And the final thing is that CSRO also plays a really important part in reaching out to the next generation of researchers, and through our education programs and the various media and magazines and things that we do, we reach a large number of schools and students across the country every year. So the thing that you're here to hear about today is this broad area of flexible electronics, and this is an area that has emerged over the last couple of decades, and we and many others around the world believe that it is really transforming the way that we're using and approaching electronics. So the specific things that we're working on are developing these technologies that apply to a couple of different specific product types, and shown here. So I'll go through these in a little bit more detail, but the organic light emitting diode here is a display and lighting technology. The OFET is a field effect transistor that acts as the switches, controls circuits, and the organic photovoltaics that generates power. So we're working on these sort of three main application areas in our work at CSIRO. And just to give you sort of a bit of a flavour for what happens in the labs, these are some of the equipment that we do. So starting with the chemistry stage of things, where we're developing new molecules, we do some modelling where we design the molecules and look at their properties using density functional theory calculations. Then we make them in the lab, and we've got some equipment that can do things in parallel and speed up the synthesis part. But we've also got the capability at CSIRO to make very large-scale batches of things. So we've taken one of our organic semiconductors up and made 1 kilogram of it, just to sort of show that we can do it and use it. And that sort of capability is fairly unique in the sort of chemical manufacturing industry in Australia, an ability to do batch synthesis of a diverse range of chemicals. But it's really important because it means that we have the capacity to produce large amounts of material. We've also got a whole range of equipment that does different sorts of spectroscopy or analysis of devices, and in recent years having access to the Australian synchrotron here has enabled us to do things that we were previously unable to do locally, and looking at the structure, what's actually going on inside these solar cells. We've got labs where we manufacture the devices, and these glove boxes and clean rooms allow us to control different aspects of the process, so we can eliminate oxygen and water, for example, from the manufacturing process and see their effects. So in combination, we've got the equipment and the facilities to be able to do this whole circle, right from small-scale discovery to scaling up large amounts of materials, evaluating the devices, and then finally, as I'll introduce, printing them on a really large scale. So putting all this together has been sort of a 7 or 8 year journey for us at CSIRO and with the partners that we have. But as I said at the start, it's been a really exciting one for me personally. I've been fortunate enough to be involved with this from the start, when CSIRO sort of moved into this area, and to be able to have things that we can touch and feel and hold now that are actual real devices has been a really big effort by a lot of people. So just to go back to the types of devices that I introduced, and we'll just focus on the two main ones, the organic light emitting diode and the organic solar cell. Now both of these technologies use organic semiconductors, so carbon-based materials, as the organic semiconductor, but sandwiched between two electrodes. So what makes it attractive is that they're very, very thin. So the organic semiconductor that we use, the total device thickness is about 200 times thinner than your hair. And so it's that makes it flexible. And we've been developing the materials and the device structures for both of these. Now, the sort of drivers for this are that we want in our devices things that are brighter and flashier, but also more efficient. There's also the desire to have them to be flexible, conformable in some way, use electronics in different ways. And the organic light-emitting diodes were first developed by Kodak back in the 80s, and they found that you could take some of these organic semiconductors, and there's an example here. This is an aluminium complex that emits green light, and as I said, sandwich them between two electrodes. And if you make a device such that you've got emitters that are all different colours, you can make up a full colour display. And OLEDs, as sort of the first flexible electronics technology, have really led the way. And there's now examples from LG and Samsung of large area solar cells, large area OLED TVs. So they're shipping 55-inch OLED TVs that are about 3 millimeters thick. And as well as being amazing to look at and really good, these are extremely efficient devices. And that's again one of the real benefits of OLEDs, in that it's an emissive technology. So compared with liquid crystal displays or plasmas, where you consume a large amount of energy to generate the light, a liquid crystal display, for example, has a white light in the back, and you're using colour filters to filter that out. An OLED display, if you want blue, you just turn your blue pixel on. If you want red, you just turn your red pixel on. So the energy savings by using OLEDs are enormous. And right now, OLEDs are the most efficient light source that we have. So green OLEDs are more efficient than any inorganic LED. And so the prospects of moving that into solid-state lighting are very good. And so this idea of moving from having point source lights here to having panels that we apply to the roof and having large areas emitting light and doing it at higher efficiency is certainly feasible. Now, the aspect of making OLEDs on a large scale, one thing that really changed that was the work that was recognised with the Nobel Prize in Chemistry back in the year 2000. And this was the discovery of conducting polymers. Now, we rely on polymers to be insulators in most of what we do. The power cords that we've got here are insulated with plastic to stop me getting electrocuted. But there are certain types of polymers or plastics that can conduct electricity. And the work that led to this Nobel Prize inspired a whole area of research around these conducting materials, conducting polymers. And one area of this was polymers that emit light. And the discovery of light-emitting polymers and their application took place in Cambridge in the late 80s. And Professor Andrew Holmes, who was then the director of the Melbourne laboratory at the University of Cambridge, and Richard Friend in the physics department, together their groups discovered that they took one of these polymers and they put a voltage across it and it emitted light. And that was the discovery of light-emitting polymers. Andrew, as some of you may know, is now back here in Australia, and he moved back at the same time that I did from the UK to lead much of what we have done here. And he's based here at the University of Melbourne with a joint position at CSIRO. And Andrew, probably more than anyone, has been responsible for growing this area of flexible electronics in Australia. So having been the founder and the discoverer of the work in Cambridge, to have him come back here and lead the work has given us great credibility and a great start in building this area in Australia. So these light-emitting polymers, they're basically conjugated materials, alternating single, double bonds, and so you can transport charges along them, but they're also fluorescent. And because they're polymers, they can be dissolved up in solvents and deposited down onto a surface, just like a paint. And it's that possibility that really changed the game for this sort of flexible electronics technologies. The fact that you could paint these materials down or coat them down opened up the way to all these low-cost deposition processes. As far as the polymers themselves go, we can change their chemical structure, and that changes the colours of light that they emit. So for those of you, that may not be chemists, this is a relatively simple change between the green emitting one here and the red emitting one here, and we can in some way predict those sort of changes. And that flows through to the solar cell work too, in terms of the amount of light that they that they absorb, as I'll get onto. So by changing those colours, we can engineer all colours of the spectrum. That enables displays and as I introduced earlier, lighting. So the reality of this is that now there are products out there. As I said, most Samsung mobile phones have got an OLED display in them now. There's these large-scale TVs coming to market. And there has been work that has been done on actually making these flexible. So this is a little video from Sony that's got some funky music in the background. But this is showing that they really have made displays that are flexible. And so this is rolling up around something around the size of your finger. So that's the OLEDs. But as a technology that's been leading the way, it's really important that we recognise that we've been building on that work to develop the solar cells. So now I want to introduce our solar cell work. And again, I'm very aware that some of you probably know some of what I'm going to present in the next couple of slides better than me. If you can use what I'm using, please use it. If you can help me put together better slides, I welcome the advice. But when I'm introducing this, in particular overseas, I always put up this slide as sort of taking some responsibility for Australia. Should, in my opinion, be taking some action in this regard. We do rely on fossil fuels for most of our energy generation, and the fact that we emit more CO2 than any other country in the world per person is, I think, strong enough motivation in itself for doing something about renewable energy. And this cartoon that I took a while ago from, I think, it sums up a lot of the thinking that happens in Australia, and we need to remember that, there's this big sun up there. There's a couple of examples that I've got on this slide about why we should do solar power, and the fact that it provides maximum amount of power at the times we need it most is foremost. And the two examples that I've got at the bottom there are things that I often relate, particularly in school visits and things. And so there's examples that I've seen of places in the world, say in Africa, that are not grid connected, where they need refrigeration to deliver medicine. And so they had these camels with fridges on them, and they've got solar panels on the back of the camels that are powering the fridges. And you think that's neat, but that's changing people's lives. That's doing something that they can't do by another means. And the same with homework at the bottom. I'm sure many of you are aware of the situation in many developing nations where they're reliant on kerosene lamps or nothing. And at the end of the day, when the sun goes down, the students or people at home, they can't read, and so that reinforcement of what they've learnt during the day doesn't happen in the same way that it does in places where we have grid-connected power. So these are motivations for doing this off-grid, on-demand power generation. And can solar make a difference? Well, you all know it can. And at the amount of space that we have in the country, we could give up this quarter of South Australia and power the whole planet. And there's not a lot out there. But even if we just say that, assume that was distributed over the whole, over everyone's roofs or anything like that, it can make a substantial difference. And as far as why Australia doing it, this map of solar insolation, so this is ground level insolation, shows that if you're going to do solar production anywhere in the world, it probably should be in Australia. We're the sunniest place on the earth. The mountains of South America mean that the clouds restrict their insulation there. And you compare us to Germany, that's got more solar installations than the whole rest of the world combined, and we're so much sunnier. And when you zoom in on the actual country, and I look up here around Port Hedland, and I'm sure you can't read the numbers, but they average about 10 hours of sunlight a day up there, average. So it's a pretty sunny place. I've got my little bit at home. This is a photo of my house out at Williamstown, and I've got our little bit. But when I was on holidays in Western Australia last year, I saw these guys they were more than doing their bit. If we can aspire to that, I think that's good. So now the organic solar cells and what we're actually doing with these and what the technology is about. So why we're doing this is that we do really think that it will lead to new applications for solar and help drive the options for renewable energy. But we really see this as it having to be through a manufacturing approach, that it's not just about saying we're doing renewables and for renewables' sake. It's saying that we can do this by developing a new manufacturing proposition for Australia. And the VICOSC Consortium that we're a part of, I guess, reflects that in coming together with the research groups that we have and the companies that work with us. Together they represent a collection of people with this focus on manufacturing to deliver a renewable impact. And so our key partners, industrial partners here, BlueScope Steel, obviously the largest producer of steel roofing in Australia. They have about 60% of the new residential roofing market now, about 90% of industrial market. So it's a pretty big player in the field. And despite some more recent financial difficulties, they still have a substantial presence overseas. And they have been a very big supporter of our project, and they will later this year have their first solar roofing material available. And so I'm sure you're all familiar with the normal corrugated colour bond pattern that you've got. Well, they've now developed a new roofing material that actually has horizontal panels to which a thin film solar cell can be applied and attached directly to the roof. Now, it's not yet our technology that's going into this. We're hopeful that it will. They have tried to work with a number of existing thin film manufacturers to develop the technology that goes into it. Unfortunately, all of those have gone bankrupt. But they persevered with the technology and are persevering with the product because they believe that the market wants this. And so their approach, they described at a meeting I was at recently as a technology agnostic product. So they're building the steel roofing panels that can accept any sort of solar cell on there. And I think that's a really great thing for them to continue to have faith in this idea so that people will then be able to apply whatever they want to it. And further down the track, hopefully, develop the capability themselves to apply it directly on there, and hopefully what we're doing. The other key partners in here is Innovia Films, who are now the parent company of what was Securency. And coming back to what I introduced at the start about the banknotes, that they were the company that now produce banknotes for about 35 different countries around the world. Their expertise, Canada is the latest country that's just taking on polymer banknotes now. And so that expertise has been translated all around the world. But Innovia are experts at printing on plastics. And they produce the banknotes at speeds of up to about 400 meters a minute. So when you go into their factory, it's just incredible, the scale of all these printed rolls going up and down and pallets of money stacked up all over the place. It's more money than I'll earn in my life, some guys wheeling around. So it's incredible. But Australia's current banknotes are actually one of the least secure of all the ones they're doing now, because some of the other countries have all different security features. There's some Vietnamese banknotes that a colleague of mine, Jerry Wilson at CSRO, was involved with developing, and they've actually got a diffraction grating printed into the window, and when you shine a laser pointer through the window, it projects an image onto the wall. And they're making that by printing. And so these guys know a lot about printing, and they have, over the past sort of 5 years, been incredibly important to us. We weren't printers. My background's in chemistry. Most of our team have got backgrounds in material science and different areas. But the guys at Securency have taught us how to be printers and given us advice about those things. So I can't emphasize enough how important that partnership has been. And another partnership that we're involved with now is this new Australia-US Institute for Photovoltaics. It's been funded through the ARENA program. It began in the Australian Solar Institute last year. And this program, for the first time, brings together all of the major groups in Australia working on photovoltaics in general. Now, I'm sure you're familiar with Martin Green's work at the University of New South Wales on silicon solar cells. And Martin has led the field internationally in this area. And he has also been very generous in his support and encouragement of the next generation technology we're developing. But now with this new specific funding that links us together with his group at UNSW and the silicon groups at ANU, as well as the groups that we already work closely with at Melbourne, Monash and Queensland, it gives us an opportunity to learn from all of the things that the silicon technology has been through and developed, and also a greater opportunity to interact with the research institutes and the companies in the US. I just got back from 2 weeks in the US on Saturday, and this was the focus of the visit, setting up these bilateral visits, these sort of collaborations to grow what we're doing and partner with them. And it's a really, really great opportunity. This is 8 years of funding. It's a significant investment from the government. So it's been a really, really great thing. So the organic solar cells that as I introduced at the start, are these organic semiconductor that's sandwiched between two electrodes. But the way that they actually operate is there's ideally two materials, one to transport the positive charges and one the negative charges. And when they were first discovered, again, work back at Kodak, and they formed a bilayer, so as shown here, where the two layers were sitting on top of each other like this. And at the interface between them, you got separation of the charges and moved away to the two electrodes. But in the late 90s, a group led by Alan Heeger, who I previously mentioned as the Nobel Prize winner, discovered that you could increase the performance of these devices by making what's called a bulk heterojunction, and that's shown here. So in this device structure, you mix the two materials together, but by having a greater surface area, that creates more opportunities for charge generation. And then what you just have to do is make sure that the charges can work their way out to the electrodes. And so the final picture here is sort of the stylized image of what one day we might hope these devices look like internally, where you've got high surface area but continuous pathways for the charges to the electrodes. So we take this bulk heterojunction here and we put it between two electrodes, and one's transparent, at least one is transparent, and then put another electrode on top of it. But that's really about it. It's not a lot more complicated than that, maybe some little interface layers on the top. But that layer is between about 80 and 300 nanometers thick, so it's really, really thin, very small amounts of material. So just to give you an idea of how these cells perform, so this is the P3HT, the polymer shown at the top here, a polythiophene polymer, is the most commonly studied material, and this is what we sort of use to check ourselves against. And so this will give an efficiency of about 3%, but this is what the voltage and absorbance properties look like. So out of a single cell, we get about 0.6 volts, and we're absorbing light out in the sort of green out to red region of the spectrum. Now, what's really, I guess, exciting about organics is that we can tune that property, that absorbance property. So the chart from the previous slides reproduced here, where with P3HT we're absorbing out to 650, but shown over here is the solar spectrum, and you can see there's a lot of energy out here, out in the IR, that we're not collecting. So we can use different organic semiconductors, as shown here, that actually absorb light more out there. And this is a really different situation with silicon, because silicon's got a fixed band gap, and you can't do much to change. You can't do anything to change that. So the amount of light it absorbs is fixed. With organics, we can tune the energy levels such that they can absorb different amounts of light, and the possibilities are really endless. We've got the whole periodic table available to us. We can put those atoms together in all different ways and tune those properties to give us really whatever colour we want. And as well as being more efficient, it also gives you the opportunity to make them in different colours. Now, the less black they are, the less efficient they are, but we often talk about organics as sort of having four things that you're sort of playing off against each other. You're playing off efficiency, you're playing off lifetime, you're playing off the aesthetics, and you're playing off the, there's a fourth one, efficiency, lifetime, and it'll come back to me. But yeah, cost, that's a good one. Cost, efficiency, lifetime, and aesthetics. And so if the aesthetics is worth something to you, you can perhaps trade that off against some of the other factors there. So put together the fact that they're thin, flexible, and that we can change the way that they appear, we think makes them a valuable technology for a range of applications. Another aspect of them is that they do give a fairly stable voltage under low light conditions, unlike crystalline silicon that sort of drops off very rapidly indoors or in shaded conditions. So that's a differentiating feature. And so you can possibly put them in situations where you just want to constantly charge a battery. Now, that's what I've presented so far as our work about using organic materials as the absorbing material. What I want to just spend a couple of minutes now talking about is some other work that we're doing at CSIRO, which is based on nanoparticles. And the two guys here, so Jack Jasenyek is been the project leader for this work over the last few years, and Brandon McDonald was a PhD student who worked with Jack and I, who was based at the University of Melbourne with Paul Mulvaney here, but did most of his work out at CSIRO. Now these are inorganic solar cells now, but it's still with the goal of making them printable. And so we're doing this in parallel with our organics, and this is for a couple of reasons, because these inorganic semiconductors, and so there's a list there, so compound semiconductors based on cadmium telluride or CIGS or CZTS. These are proven technologies, that some of which are already in the market. Now, at the moment, they can be put down onto metal foils, and printing them down gives you the benefits of it being a continuous process, and then you can also make it fast, and that means that it's cheap. But at the moment, we have sort of pretty primitive control over the purity of the materials or of the vertical structure of these devices. So the way to sort of, or a way to address this to enhance the problems that we have about low efficiency is to use these nanoparticles. And there's a few different approaches to using nanoparticles, and you can either make them in solution or make precursors to them. But what Jack and Brandon developed was a process where we could take these nanoparticles in ink and deposit them down in a film to make a solar cell. So all from solution, all in air. Now, what's going on inside these particular devices is that they made these nanoparticles, and in this case, these were cadmium telluride. And shown over here is the cadmium telluride nanoparticles with some ligands around the outside to make them soluble. They then put them through a very quick chemical and thermal treatment, and those particles start to grow a little bit bigger. And then we put another layer down on top and do a little chemical and thermal treatment, and then they grow a little bit bigger. Now, by doing this layer by layer approach, we stop cracking or the films developing defects. And the end result is that we've taken our 4 nanometer nanoparticles at the start and turned them into 70 nanometer crystals. Now, at that size, those crystals have about the same properties as the bulk semiconductor. So we can make these inorganic solar cells from solution, from the nanoparticles. And we end up with a film that's much thinner than the devices that are made using traditional ways, which is by closed space sublimation. As far as the performance of these go, we've made a few other changes, and this is the sort of structure that we have to them. But we've now got these devices having efficiencies of about 10%, which is comparable with what people get from much thicker devices, but it's a simpler manufacturing process. So again, this is a proven technology that we're developing a new low-cost process to make, where it's all from solution and all in air. So we think that this goes in parallel with our organic work about developing materials and processes for printed solar cells. So now on to the printed solar cells themselves. So since 2012, we really started in earnest actually printing these devices. And I brought a few along. So these were sort of the size that we started off printing, where the printing width was about 10 centimetres wide. And then gradually over the last couple of years, we've moved up to doing it a little bit bigger. So what I'll show you here is sort of a little bit of the journey of doing that, and talk you through how we've made them. So, as I said, the first printers that we had gave us this 10 centimetre wide width, and we could see we're printing it down there, printing these lines of the different semiconductors onto it there. We printed meters. We got the best looking guys we could find in CSIRO to model these, really hard. But we printed lots and lots of them and learnt a lot how to do that. We did a lot of testing in terms of outdoor usage, and this is showing you that you can see through them and stuff like that. Making little demonstrators to put into people's hands to show things and stuff has been really important, so that we can show that it really is real. We did a lot of outdoor testing, and we've set up that rig that I showed you there to mimic the north, south, east and west facing sides of a building. And we linked all that back into a computer where we can monitor the absolute performance and the irradiation. We can also measure them under different conditions of different humidity, temperature in these chambers, and get a wider range of conditions. We made a whole lot of cells that we gave away to one of the university classes up in Sydney, the University of Technology, where we use them in our undergraduate classes. And then we started printing on a bigger scale. So this was the next printer that we bought, about 30 centimetres wide now. So the lessons that we learnt on the 10 centimetre wide, we applied to that. And then finally, this is our largest printer now, which is about 14 metres long. It's a dual head screen printer that enables us to put down the electrodes on top of that. And so the final shot there that I just put in is sort of linking this back to the money, where we started. And I'll pass these are a little bit battered. I've been carrying these around the US with me, so they look better than that when I started. But you can have a look and feel and see that they're real. I forgot to bring a light. I bought a fan, but I'm sure this cell's delivering plenty of voltage in here, but it's not quite enough current under low light conditions to show you in here. So we've been putting these together now, as I said, in earnest. The large scale printers that we took delivery of that earlier this year. And it's the really large one, the 14 metre one. It's a dual head screen printer, so it's just like printing t-shirts. So we make up screens. They cost about $50 a screen. We tell them what patterns to put on the top, and we apply the ink, and it's just put down. That printer was designed to print paper, and so there's really nothing fancy about it. The total installed cost delivered to the door was about $200,000. So when you compare that to a silicon fabrication line that costs about $1 billion to set up, it's pretty cheap. And so we really think that this is, we've got pretty good evidence that this is a low cost, low barrier to entry manufacturing process. The printer, it was a really nice story about how we got that printer and perhaps did the installation. And there's a company here in Melbourne, Conway Engineering. A guy, Robert Conway, has run the printing company all his life. And they mainly specialise in making the shade cloth hoardings that go around the outside of buildings. Print company logos on them, things like that, when they're construction sites. And we were introduced to Robert through some of the contacts in the Victorian government. And we went out and we told him about what we were doing, and he came and looked at it, and he sort of said the precision that we're trying to do, which is not very high compared to what he was doing. We're printing 1 centimetre wide strips endlessly. That's pretty easy for him. So he was able to sort of look at what we were doing, and then he introduced us to some equipment manufacturers that were doing something that would make the sort of devices we needed. And he then served as our agent and our sort of local installer to help us set up this equipment. And so it's been a really nice story of someone who's a genuine, real printer helping us do this new technology. Now, as far as the performance of the devices go, this is our story again over the last few years. And Michael Brown, who was employed here at the University of Melbourne, made this figure, which I think sums it up nicely. So when we first started the printing, we weren't very good. The efficiencies weren't very high, and the area under the curves in here is how long they lasted. So they didn't last very long. But now, on terms of our printed devices, we've got the efficiency up to about 2%, and we're seeing lifetimes of these devices now out over a year, and that's devices we made a year ago. So hopefully the ones we're making today are better than that. And this is all the printed ones, all on plastic here. So the things that are impacting on that lifetime is really about the barrier materials that we're putting on top. And we're constantly trialling new materials and new ways to seal them up and stick them together. But the sealing process is just lamination. So in the early days, we just bought a laminator from Officeworks, and it was literally just feeding it through the laminator. Nothing more complicated than that. That's what it will be. In the future, it will just be a different material that will be laminated. So as far as the actual applications go, this slide illustrates a few of the directions where we think we'll go. And what we make the argument is different about these printed solar cells compared with other renewable energy technologies is that there's this staged range of applications. We're not going straight to the grid. We can't do that just yet. But we think that because there's these staged applications, there's an opportunity to get different sorts of companies to invest in the development of them and to provide an actual market along the way. So some of the earliest applications that we're in very deep discussions about now are in in-store applications, in advertising. And so it might be that in the not too distant future, some of these printed solar cells are embedded in the top of a cardboard box that's in your supermarket that beeps at you when you go past and tries to encourage you to buy more chocolate. Now, that's not going to change the world, and it's arguably a negative thing, but for us, it's an opportunity to get something into a product and to learn about yields, to get some more investment, to build some more momentum about the technology. And the amount of power we produce, the lifetime we can do, matches in with that application well. Moving on to the next sort of phase, outdoor, shade cloth sort of things. We've spoken with companies that make temporary shelters outdoors, like on mining sites, where they might only need to be there for 6 months or something like that, but they can't, they're very flimsy shelters, they can't put silicon panels up on there. So again, a great application that's staged in terms of what we can do. And then I mentioned earlier the work that BlueScope Steel are doing. That's obviously one of the long-term things, and also talking with a range of different companies that might integrate the solar cells into building materials, and that might be glass, so that could be splashbacks in your kitchen that are doing things in there, indoor. It could be glass paneling in offices for privacy screening. It could be parts of windows. So it's all those sort of things that we think there's this whole range of different applications that we can work on that can help drive the technology. And this roadmap was put together by the Organic Electronics Association, which is an association that we're part of that links research institutes and companies around the world. And this is sort of, I guess, spelling out that same sort of strategy, that these sort of staged applications, increasing in performance and complexity, is the roadmap to deploying this technology. So now, I guess I've just got a couple of examples here of, this is some work that we did in collaboration with the Danish National Laboratory, so at Vize. So Frederick Krebs is a guy there who's been incredible. He describes himself as probably having made more organic solar cells than anyone in the world, because he's printed lots of devices. But we've worked with them on a few different aspects, and one pilot study that they've done addresses this issue I raised before about lighting in replacements for kerosene lamps. And so what they did was develop these little printed solar cells, much like what I passed around here, and they had a little battery integrated in them and a light, and the people could leave them outside during the day, charge the battery up, and then provide light in the evening. And that, far more than the chocolate box example, is something that's actually worthwhile doing. But again, it's an application that's probably within reach now for the technology that we're doing. So, to put a few summary points around the value proposition for this, we think that it is inherently an inexpensive manufacturing technology. It's low-cost deposition processes and very small amounts of materials. And as I mentioned, chemistry gives us the opportunity to make a whole range of different materials. So there's huge diversity. We're not talking about a single semiconductor. We've got demonstrated significant lifetimes. I actually didn't mention in the lab we've now got some of our own organic polymers that are giving efficiencies of up almost 9%. So that's constantly evolving. And we do firmly believe that these early products will be in these simple applications, but they'll evolve into larger products that are on the way to large-scale power generation. And one of the things that I want to emphasize again is that we really believe that this technology will be advanced by the printing industry and the electronics industry, as opposed to the energy industry. We're not really that applicable to the existing energy generators, but the technology we're developing is really applicable to these electronics companies. And the size and the diversity of the display and lighting market, and going back to the OLEDs that I introduced right at the start, is a really significant advantage for organic photovoltaics. Already the OLED market is bigger than the entire solar cell market, so the investments that companies have made in that OLED technology can be easily transferred to PV and advanced in that way. Now, I said at the start I'm here representing the group of people that's done this research, and it's really important. I've mentioned a few of them along the way, but to acknowledge their work. And this is the team working on flexible electronics at CSIRO that we've put together over the last few years. And there's people with backgrounds, as I said, in chemistry, material science, physics, and more recently printing. And we've really benefited from having a huge number of people from all around the world come and work with us. That benefit, though, does highlight what I want to finish by talking about, and that's the people development, and it's another big aspect of what we're doing. it's been great getting these people from all around the world to come and work with us, but it's also, if we really believe that this technology has an opportunity here in Australia, we need to be developing more people trained in these areas here to be able to do those jobs. And one way that we can do that is by communicating that there's an opportunity in this area, that there is good reason for going to these areas of study. And so part of that has been our aim in some of the work that we've done about science communication. So earlier this year, and probably the reason why I'm standing here, is we did a press release where we deliberately reached out to the media about what we were doing, and there was some trepidation about that. We don't often do this sort of thing, and really, as scientists, blow our own trumpet sort of thing. But so I just wanted to show you the video that we made and talk you through a few aspects and some things that we learned about this. So this was the video that we made, that we served out to the news agencies.
We're really pleased to commission what is now Australia's largest facility for printing thin film solar cells. This equipment that has been purchased over the last few months and commissioned in our labs here in Melbourne will enable us to print A3 size solar cells. We've rapidly scaled up making our devices from fingernail size in the lab to A3 size devices that are fully printed now. And at this size, we're definitely up there with the best in the world. In the short term, we're looking for applications in consumer devices and small integrated electronics. In the longer term, we see these materials being able to be coated onto buildings, into windows, and on roofs to provide power in a wide variety of locations and circumstances.
One of the advantages of the technology that we're developing is we're actually using off-the-shelf printers you can go out and buy, and therefore we're using a screen printer, one that you would normally use in label manufacture or screen printing of t-shirts or other things. So these are commercially available printers. So the outcome of this will be prototype demonstrators that we can give to a number of people to examine what the capability of the new technology is.
I do see this project as a very good example of a collaboration involves the CSRO, Monash University, and Melbourne University, and we have a very close collaboration with people working at each other's laboratory, and we have regular meetings every 2 weeks. We do see that through this kind of collaboration, and we can build up a critical mass, and that will be very, very helpful for a country like Australia.
What we're doing truly is additive manufacturing. We're taking simple substrates such as plastic or steel and coaching them and turning them into solar cells. This is what a factory of the future looks like, and it's based here in Melbourne's emerging manufacturing precinct.
So, so for us, it was something new and we hadn't done before. But the impact of it was beyond what we could imagine. I mean, the reach that we got, particularly through social media, was enormous. This was the most popular story that CSIRO has ever had through Facebook. We reached an enormous number of people through Twitter, done dozens of radio and podcast interviews, and still I would still be getting an email every second day from someone. Oh, I saw this in the press release. So this was, like I said, something different for us. But the biggest impact that it's had, there's a lot of goodwill. A lot of people think we're doing good stuff, and that's really great and important. But what it has done more importantly is connect us with some companies that are doing things that are relevant here in Australia. And these were companies that we didn't know what they were doing, and they didn't know that CSIRO was doing this sort of research in Australia. So there's a company in Adelaide that makes lighting products, and they heard me on the radio over there in Adelaide and rang up, got on a plane a couple of days later and flew over here. So there's probably about 6 or 7 companies now like that we've been speaking to, that we're really hopeful of translating some of what we're doing into real products. And we wouldn't have had those connections but for this outreach through the media. In terms of the lessons learned, I think the video was incredibly useful by serving it up to the world. The news agencies like AAP took it, repackaged it, that got it into all of the Fairfax newspapers, that sort of then snowballed into radio and things like that. And then things like the Mashable blog. I mean, Mashable, for those who don't know, is one of the biggest tech blogs in the world, and the fact that we got a story in there was great, and then 8,000 people read it and decided to share it through their Facebook pages and stuff. So that was something that we hadn't anticipated would go that well. And as I said at the start, it was something that we did with some trepidation. Most of us, particularly in academic sort of research, are comfortable publishing in journals, and we lose control if we go to the media. But by speaking to people through the technology, through the media that they were comfortable with, we were able to reach people. So as well as conveying that message to potential partners, we also think, as I said at the start and is here being summarised at the end, it's about growing the capability here in Australia and encouraging people that this area of research is one worthy of choosing in Australia. And so if I'm so bold as to sort of suggest things to people involved in education, I say that scientists trained in all aspects of communication are really important, and the different cross-curricular activities that people could do, incorporating science communication in them, I think is really important. And I mentioned briefly before, we've done one pilot project with UTS where we printed a whole lot of solar cells and we gave them to their undergraduate physics class, and they did experiments on it, and that was really successful with them. I did a video linkage in with their class where I came in on the projector and talked to them, and we're trying to interact with people in different ways, and hopefully that will drive that enthusiasm for studying the chemistry of materials and material science in the future. So just to wrap up then, what I've presented to you tonight, in terms of the technologies and our approach to it, what we've put in place is a whole range of different things in CSRO and our partners, from developing the materials right through to printing them and testing them. And by having this circle, that's what's really unique about this approach that we've done. There's other groups around the world that are working in this area, and we do have close collaborations with them. But I think having in one consortium the ability to go from new materials development all the way through printing is what's giving us this opportunity to accelerate that cycle and really advance the technology. So more broadly, I guess we really believe that flexible electronics is something that can have a place in manufacturing in Australia, and that this staged range of applications is the roadmap for the solar cells here. We can do it, we can print it here. We've come a long way. We've still got some way to go. We need some people to work with us on that journey for that last little bit. But we think that we're well positioned to do that. But the final part that we need there is to train people to be able to do it. Now, the final comment that I'll just choose to make in a forum like this is something that a point that I heard Nate Lewis from Caltech make a few years ago. And in saying this, he mentioned this at this point, and I mean no disrespect to people that have suffered through things, but cancer is a disease that is a terrible disease and very tough for people to deal with. But as a planet, in 20 years' time, if we have not cured cancer, the planet will largely still be the same. It won't have changed much. But if in 20 years' time we haven't developed some better ways of generating the energy we need, we will, under all estimates, have irrevocably changed our planet. Now, it's not about a competition between solar cells and cancer research, but it's about saying some of the things, the approaches that we take, the way that we fund that sort of research, the importance that we put on it. Maybe we need to consider whether that balance is right or the way that we approach it is right. We're trying to develop something here that has an impact in renewable energy generation. We believe that to do it, we have to do it as a manufacturing proposition for Australia. And the interest that people like you have taken in this is really heartening for us. We're excited by it. We're really proud of what we've done. We've got some way to go, and we hope that you can help to continue support us on that journey. So thanks for being here tonight. Thanks for listening to me. It's been great.
Thanks very much, Scott. Has anyone got any questions?
Fire away.
Is temperature a real issue with the substrate?
Organic solar cells actually have a positive temperature coefficient. They actually perform better under high temperatures compared with silicon, which drop off under temperatures. Now, the limiting factor in what we're printing is the PET, the substrate, and that's stable up to about 140. So our outdoor testing, based on what BlueScope taught us, is that their roofs see about maximum about 80 degrees Celsius, so that's what we aim at, and to 80 degrees we're fine.
Could you go one step further with this, and you've got organic fence? Could you come straight off the roof as I see?
Yeah, that's possible. I mean, we have had a little bit of thinking about, incorporating inverters into the side of things. I think we need to solve the printing things first, but the alternative, why can't you run your house off DC? So.
Just strikes me that one of the major impediments to this happening on a wide scale is the lack of, almost total lack of plausibility amongst politicians that this is even possible, let alone that they want to do it. And they're the ones that sort of lead public opinion in this in a way. I'm wondering how much luck or success have you had in dealing, in communicating, not just with kids at school, which is a pretty long-term process, but with a current batch of politicians or the ones that are on their way through now.
Yeah. Well, I think, the funding that we have received from both the state and federal government has been repeat funding, and both, if we take the Victorian government, in the course of the project we've had a change of government here, and they have continued to be very supportive of what we're doing. I can't speak highly enough of that support. So I genuinely think there are people in government that do believe in this.
Likewise, with the heat, how do they perform in the shade? Like a normal array with a shade, a patch of shade,
you get a big drop off. Yeah, and look, it's still light in, energy out, but they maintain a pretty stable voltage under even low light or shaded conditions, and so that's where you can design it in that way. And another aspect too is that we can print the devices in any configuration you want. So the device that I'm passing around there, they're all in series connection across there, but just changing the screen means we can print half in series and half in parallel or whatever, and it's just changing the screen. So it's a really simple thing to do.
And will you still need electricians to install them and things like that? Or
I would imagine still, yeah. I mean, so long as we're generating enough power, which we hope to be. So, yeah.
That story you said about going on the radio and that lighting company, in a broader question about CSIRO or maybe science in general, do you think that you're marketing broadly enough what you're currently doing so that people out there realise what you're doing and hence can get on board early enough, or is your particular project more commercialisable, so to speak, than maybe most of what's going on?
I think we could all do a lot better job. Me included, all of us as scientists need to do a much better job at putting the message out there and doing it, and making sure that we're solving problems that are genuine problems and not just doing research for research's sake. It's hard. We employ people because they're scientists and they're not necessarily good communicators, and we all, me included, have to learn. So, but we could definitely do a better job.
I'm just curious why you've now gone to A3 sheet printing. Because you had continuous printing before. I would have thought that would be a more economic thing where you can just keep changing stuff back continuously.
Yeah, it was a decision, I guess. It's partially perception. We sort of set our goals early on to be able to produce sort of A3 size things or something like that, and 10 centimetres we were showing people, and they're like, oh yeah, okay, that's all right, sort of thing. Now, in an actual product, it might be that the 10 centimetre wide one is okay, but I think the impact of going to the larger scale, when it's perhaps hard to get the scale from the video, but when we take people into that room with that 14 metre wide print, it's almost as wide as this room, universally their reaction is, okay, you guys are serious. This is actually a serious effort at manufacturing, whereas the 10 centimetre wide printer is about the size of this bench, and it's in the fume cupboard in a lab, and it sort of more conveys, it's still at the research phase. So some of it is perceptions, but also there's many applications that we think that do need that. We don't need to go any bigger than that. I don't think there's any call for it.
It's actually continuous at 30 centimetres.
Yeah, totally continuous, yeah.
What's its mechanical strength like? If it's raining and a decent sized claws land on it, it's pretty thin.
Yeah.
What's its?
That really depends on the substrate. So the PET, we're just putting a very thin layer on the top. So we've got some grades of the PET that's very thick. I mean, you imagine your Coke bottle, that's pretty thick PET on there. We're not. We can print on anything. We can print on metal foils that, like I mentioned a couple of times, would have much stronger properties. So yeah, that's something that we would fit to the application, depending on what we do. And there's even work that we're doing about flexible glass. You know, there's these new types of glass that Corning and Asahi are developing, where it's, you know, glass that you can actually bend and roll around your finger. And that's just amazing. It cracks a bit, but they're working on it. They assure us that they're solving these problems.
Yeah,
but
it's the cracking or the it's clawing it, whether it's rip it.
Yeah, but I think for many applications we can solve that.
Do you foresee this as being eventually like a home printing application of this? Like you can now buy home 3D printers?
Yeah, I mean, it's not. That's not beyond the realms of possibility. You know, whether that would make sense and be the most economical way to do it, I don't know. But you know, we don't inkjet printing, for example, or 3D printing that people do is about precision and putting down specific things. It's really a coating technique that we're doing, large areas. You know, the 1 centimetre wide strips on those things. So it's not hard, and if people want to do it at home. Yeah, there's not a big barrier.
I'm picturing an electrician turning up to do an install, and he's got a printer in his van and he prints your roof.
We'd love to do that. We'd love to send a shipping container around the world, and rather than you know, sending a container of solar cells to some developing country, send them a printer and say, you know, do it yourself. You know, upskill your people.
I think the inkjet has the speed potential to significantly, depending on how you need your land to go. But I mean, I've got.
Yeah, it's. I mean, inkjet I think has some really opportunities in maybe on the electrode, but for the coating of the actual thing, you know, we did, and the field in general has evaluated a range of things, and I think where inkjet's really applicable is in the OLEDs, where you want to put down pixelated things, but just for large area coating, it poses some problems in terms of not getting sort of dots or uniform coverage across a large area, but it's, you know, it's very important.
In the back row.
One set of question. It's sort of three questions, but it all converges on one point. If you were to run an average laptop, how big an area would you need, and what would that area cost?
Yeah, so I mean, we sort of say, okay, you know, your charger for your tablet or something like that, say a 10-watt charger. Yeah. So we could probably make a 10-watt cell in the next couple of years. It's maybe about the area of the cover on the tablet. So it will sort of work out, an hour in the sun will give you an hour extra battery. That sort of thing is feasible. Now, cost-wise, people have done projections that show that when done at scale, these things could get down to below the $1 a watt. So if you're talking about a 10-watt thing, you'd be below $10 for that sort of thing on the front there. So that's the sort of economics that we think are achievable.
Down the front here.
Yeah, if I was to run your A3 width, 10 metre cut or whatever, what method do you use for collecting the energy? You know, joining the wires on them. How do you do that?
So the way that it may be easy to show you on this, the way that these strips are printed is there's a series connection. So it's a staircase. So each cell is connected to the one below it, and then just the copper strips are at the top and bottom here, and they're the connections. So. And that's the same on the one that I passed around. So you just solder a wire into there, or inkjet print a wire onto the top there.
So those two connect, one's positive, one's negative.
Yeah, across there. But as I said before, we can print the device in any way you want to change that pattern, or anything. That's just changing.
And also, if for some structural reason there was a bit of stretch in that long piece. Is it able to stretch very much without breaking its internal connection?
Yeah, there's different sorts of approaches to that. One of the groups that we work with in Japan has actually made some polymer solar cells, and there's some really cool videos on YouTube where they've done them on very stretchable materials, and they stretch them sort of 10 times their initial width. Because the material is so thin, so long as you're still maintaining a conducting pathway there, it's not brittle and shatters or anything like a crystalline semiconductor would.
Right. So that means if if I had like one of those that's connected in series, and I accidentally got a hole in it or something, which has upset the series connection, that would damage the.
Yeah, you could certainly design patterns to maximise the redundancy in the cell.
Third row. Yeah.
Which one's winning the race at the moment, these or the nanoparticles?
The nanoparticles have got higher efficiencies, but we've printed the organics on large area. So, and it's really about us, I guess. The nanoparticle stuff began later and has accelerated really quickly, and we're talking with different people about that. So there's existing manufacturers of CAD telluride cells that we're talking with that might be interested in adopting that. So it's not a competition between these two things, or with silicon. You know, we think them.
What's the internal impedance like? Do you lose much of the energy in the material?
The major loss point is actually at the electrodes. So on the printed devices, the indium tin oxide is we buy in, and it's the sheet resistivity of that's actually the limiting factor in the whole device. When we buy it on glass, we get sheet resistivities of about maybe 5 to 10 ohm per square, but on the PET we're sort of 20 to 50 ohm per square, and that's what limits us to these 1 centimetre wide tracks too. So, but you know, there's people working on that. We're not addressing that. We have to focus on the key areas that we can. But as people develop, and there's a lot of alternatives like silver nanowires and carbon nanotube and graphene and a whole lot of other alternatives to ITO. There's no shortage of options in that regard.
So in terms of like the roofing to a bluescope, how do you envisage it passing it to the roof, or is it got a separate adhesive in the back, or like they're two separate material on that?
Yeah. So they've actually got a lot of experience with glues that will stick to their roofing material. Ideally, you would make it in a continuous laminating process as part of the steel production.
So they would make it in situ then?
They would ideally like to do that, but if not, you make it two separate things and you glue it on. And they know the properties of their steel well enough to know glues that are going to stick on there for 20 years.
But differential expansion in heat and cold creates a major problem with most glues. They are a little risky to use for that reason.
Yeah, I think in that case, I mean, I just defer to their expertise. They've got some set up on a thing up in Wollongong where they've had for about 2 years now, and they're measuring that. I think, excuse me, it's probably something that they can solve.
Because companies in America are commercialising now the matte style arrays. Now, can you apply what you've done to that large scale carpet matte format?
Yeah, I mean, there are examples of solar shingles and stuff in the States that people have done, and the technology is directly applicable to that. Yep.
Directly.
Yep.
Do you have any idea at this very early stage what the energy decreases over the years? So it's no silicon panels that are about 12 years.
I guess the only data that we've got is what I showed there, where we've got pretty stable current out over a year now. I mean, the degradation pathway that we're seeing tends to be catastrophic. So we've got a fairly low reduction in current and then a big drop off, and that's typically due to a mechanical failure, ingress of oxygen or water through the barrier material there. But if we take the OLEDs as an example, and I mentioned this specifically, but people have made OLEDs now with lifetimes of like 300 years. So I don't think there's a problem here. That's the same. It's an organic semiconductor that you're putting electricity through. So it's I'm pretty hopeful about that. Okay.
So are these going to replace silicon for large-scale solar farms?
Look, if everything goes great, we'd love to. Imagine sales of things all over the place and everything. But I think, like I said before, this is not a competition. So silicon, solar in general is like 1% of the world's electricity at the moment. So there's plenty of room for everything to grow. Silicon will probably always have an efficiency advantage and certainly a lifetime. I think it's going to be tough for organics to get a 25-year lifetime. Maybe the balance of systems or the rack that it's sitting on or something can be the same, and you're just rolling a new sheet out, and then this is 99% PET, so you can recycle it like a Coke bottle and use it again. So we're not seeing it as a competition, but one of Jerry Wilson, who works at me, who leads the whole flexible electronics group, he always makes the point. He says, that the chart that I put up showing the insulation over the world, there was also a really hot spot in the Indian Ocean, and plastic floats. So put it out there. Jerry will like it that you all laughed at that, by the way, I'll tell him. So.
I'm not a scientist, I'm a simple medical doctor, so I just wanted to make a comment and then a question. So the comment was around a comment about cancer treatments and things, and I'm a member of Doctors for the Environment Australia, and we absolutely, members believe that you can have the best gene therapy or whatever in the world, but if we don't have the basics, clean air, water, food, etc., that's the public health problem. So I just endorse your comments in that regard. My question was a science question about your final comment there about trained scientists and engineers, and I know I would have thought, there's a whole university here training a whole lot of people, and I'm just a bit surprised that you're indicating perhaps that there aren't people coming through.
Yeah, I mean, it is a real shortage. I mean, if you look at chemistry, physics and maths enrolments, they are dropping across the country, particularly in these sort of areas. There's probably a steady enough flow of people in chemistry and medical-related research and things, but there's not a lot coming through. And I think more importantly, we read a lot about jobs going in manufacturing in Australia, but when we talk to a lot of manufacturers in Australia, they say, gee, it's really hard to find good people in, with the skills. We talk to little electronics companies, they say, gee, we'd love someone who just understood Ohm's law or something like that. So, there is a mismatch. There is a mismatch between what's reported in the media, and I don't want to, offend anyone who, might be out there looking for jobs in this area and stuff, because it's not, the match is not perfect. But I genuinely feel that there are opportunities here, to train more people and put them into these sort of fields. I mean, give you one example. I mean, last year, I wonder how many of you knew Boeing down here at Port Melbourne employed 400 engineers last year, new positions. Now, that's not in the media. You hear about Ford shutting down at Geelong, but the same week Ford shut down, Toyota put on about the same number of employees at Altona. So the media, is selective in what it reports in manufacturing jobs in Australia, and we do get this feedback from manufacturers that a bigger base of trained people would be of interest.
When you talk about jobs there, has anyone done any sort of blue sky economic analysis of potential here as to what kind of jobs might be created? Because that's sort of a big emphasis these days, is creation of jobs in Australia for people that do.
Yeah.
About new careers in science or so forth. It strikes me that you've got printers and all the other sort of people, ancillary people, storemen and everything that goes with a whole range of new industries that are possible. Anyone done any blue sky analysis of that?
We haven't got solid data about that particular aspect of the question, but something that we did about the broad area of flexible electronics last year, there's a group at the University of Technology in Sydney again called CENSOC, which is a Centre for Choice, I think. And they, together with us, put together a survey that we did about 2 manufacturers and companies in general in Australia, asking them about their general knowledge of flexible electronics and their interest in the sort of area and stuff like that. So we put together this survey, and the results of it, I guess, gave us a very strong, clear conclusion that there was a very strong degree of interest and much higher than what we would have probably anticipated at the start. But yeah, we haven't got any data, or there's not data that I'm aware of that directly translates that into job numbers.
That captures the public imagination and the press and all that sort of stuff.
Yeah.
Talk about jobs that might get created and the economic benefit to Australia.
Certainly the government programs that we have at the moment, both at the state and federal, that's one of the major things they want to know. How many new people have we employed on the project? And they want to be able to say, the Victorian government gave $3 million for this, it was matched by $3 million. Over 3 years it generated 60 jobs. And so, and they're the sort of numbers that we've done. We've had some really nice examples within our consortium of people doing a PhD at Monash, then a postdoc at Melbourne, and then a research position at CSIRO, and then a job at Security. And so we sort of, got people going through this whole system of our partners and generating real new jobs here.
I'm involved with a group of technology development companies in New Zealand, and I'd like to tell them what you told me tonight.
Yeah, by all means.
I don't trust my notes very much. Could you point me at some information that I could pass?
Yeah, well, certainly I'm happy to take your details and send things on. I understand. I mean, we are filming this tonight, and I think this is going to be available on the website too. So I can give you the short version, or if they're really patient, they can sit through and whatever an hour of me talking again. But, yeah.
One more at the back.
I was just kind of curious. Wearable electronics are going to be a massive wave coming through. You've got Google Glass, Apple iWatch coming out, and then basically Bluetooth linked devices that need their own batteries.
Yeah.
So you've got a potentially wearable power source, and it's flexible. But how flexible can you go? Because if you could integrate it into the fabric of a clock or something like that, and it's actually charging those kind of devices, that strikes me as a huge potential market.
I mean, I agree totally. There have been some academic reports of people making threads of things, so where you've actually got a thread and the solar cells around the outside of it, and you can weave them together. You've still got to sort of make the connection and stuff, but it's possible, that sort of thing. But basically, any sort of substrate we can probably deposit on eventually. We need to solve the issues of the electrodes and some protection things, but the inherent flexibility of the technology is really only limited by the substrate. So, like I mentioned before, they're so thin we can flex them in different ways and bend them over different radius of curvature and stuff like that.
Separate to the substrate.
Yeah, but no. I mean the substrate's always going to be the limiting factor because it's so much thicker. The substrate is probably 100 to 200 times thicker than the active layer. So when you're bending it, that's the bit that will break first.
Lucas, right at the back.
Sorry, I'm not a scientist either, but just mentioned that ARENA funding. The funding you get from ARENA is related to the story that there was funding for ARENA going to be cut by the coalition government.
I sort of mentioned at the start. I mean, being a government employee, I'm not. I can't comment on particular policies and stuff, but the funding that we have at the moment is already been locked in and contracted and signed up. So, yeah.
Yes.
I'm a physics teacher and teach kids as well. Is there any way we can get hold of some of these things for my kids to play with?
Yeah, so that I mean, thank you for the interest. It's something that we're trying to put in place, that sort of thing. So what the program that we did with UTS, we actually got some funding through them where we got a guy and he just came into the lab and just worked printing a whole lot of cells. The problem we have, we've got these printers, but most of the time we're actually doing experiments on them and changing things as opposed to production where we're just churning things out. What I want to do, and I'm certainly happy to take your details and stuff, we are talking with a few different educational sort of network bodies here where we want to say, well, look, but for a little bit of extra funding where we can say to someone, that's your specific job, and just churn out these devices and give them away, we would love to be able to do that. So yeah, we're trying very hard to be able to do that.
Just in front of that person, please.
This is just a general question. I'm not a scientist here. Do you have any predictions around how many years away we are if you were to coat an entire roof of a house that it would get off the grid?
So, I mean, if you wanted to go off the grid today, I would take your silicon solar cells that are on the market now and buy your lead acid batteries, and people here might have different ideas about that. So I think that's achievable now with existing technologies. The answer to when is there going to be a product, we think we're ready to do those short-term advertising type applications now. The roofing application, we're still 5+ years away from probably having the lifetime that people need to put onto the roof. Now, whether we, with the organics, could generate enough power to go completely off the grid probably depends on the house. I'm doing my bit. Our usage is about 7.5 kilowatt hours, a day, but some other people are more like 30. So it depends. Yeah. So.
Do you have much of a conflict between trying to be open and working with other groups, and also trying to maintain the confidentiality of all the stuff that you're generating so that you can sell it later on?
Yeah, it's something we have to be mindful of, but in general the community that we work with is pretty open and collaborative. I think the things, we've got a few patents around particular types of materials that we've developed, and some device architectures that we think might have some value to some companies, but probably the most valuable thing that we've developed here is the know-how and the expertise about how to put it together, how to use the printers, all the thicknesses, the speeds, the coating densities, all these sort of things. And that's the sort of stuff that we would hope to be able to go into a co-development project with someone and transfer that knowledge to them in return for some, ongoing relationship or royalties or something like that. But in what I'm presenting to you today, I can tell you all that I've done without giving away anything really confidential. So I think we're able to balance that sort of thing up.
Yeah, is it just going to be a continuous process of this collaboration and with existing corporate entities and perhaps tendering out, or will there be actually a company set up specifically to manufacture and market this technology?
It is a tough one. I think in the Australian context, sort of venture capital funding for a brand new company to take something through in this space is hard to come by. We're open to it. We have discussions regularly with people. The feeling is that the easier path is through an existing manufacturer. So going through someone like BlueScope that already have a product, already have existing sales channels, things like that, might be an easier way. Or like the other companies that I mentioned that actually produce existing lighting solutions or things like that might be an easier way. But we wouldn't rule either out. There's examples around the world. There was, some of you might know, there was a company in the US called Kanaka that did go down the route of a startup company, and they probably spent about 10 years developing organic solar cells, and they actually printed devices very similar to what we're doing, got to about the same point as what we did, had a couple of products, but by that stage they burnt through something like $110 million in venture capital, and the investors just couldn't sustain that any longer, and so they did go bankrupt earlier this year, and that was a real blow for the field. They'd changed business model quite a few times in that time, from being a material supplier to being a product supplier to being a collaborator. So we're hoping that we can try and learn from that a little bit. We're starting further down the track than where they were, but there's no right or wrong business model. I don't think we're open to all of them.
Is that a question?
Yeah. How clear can you make this material when you're putting it on glass?
Yeah.
How much light do you lose?
Well, there is actually work that people have done in universities in actually making totally IR absorbers, and so it's almost just sort of a grey sort of tinge through it. There's a paper that was out in, I think, Science last week from some UCLA work that they had done stuff with fairly high transparencies by making these IR absorbers. So obviously, like I said before, the less black they are, the less efficient they are, but you can trade that off to a large degree by making something that just absorbs out in the IR. Yeah, that's definitely feasible that way.
Up the back there.
Yeah, just to follow on from that last question, is there any potential to say have several or two or several layers, one transparent getting the IR and one getting behind it getting other spectrum?
Yeah, very very much so. And indeed the highest efficiency reported organic solar cells so far are tandem devices where they have two organic semiconductors printed on top of each other to absorb different wavelengths of light. And another sort of idea that's sort of taking hold in the community at the moment, based on some work that Mike McGee here, who we work with at Stanford, did, calculations, was sort of saying both silicon and SIGs, inorganic solar cells, they are very poor absorbers in the blue region, but most organics are pretty high. Now, most silicon solar cells at the moment are around the 15% mark commercially, and people are trying to get an extra 0.1% out of it. But Mike did some calculations where you could put an organic solar cell on top of a silicon cell that captured the blue light, and you could probably get about a 4% increase, so 15 to 19%. And that sort of thing for silicon and SIGs is pretty big. And so we could almost piggyback our technology literally on the back of some existing solar cells by taking advantage of this tunable absorption for organics.
Very little extra cost.
Yeah. And you know, it's a great substrate, it's glass, so it's better for protecting.
The existing grid that's on the back of the silicon.
Yeah, you know, so that's, you know, that's a really attractive model. There's a few technical things we've still got to improve a little bit. I mean, you can do the calculations about the cell needs to probably deliver about 1.2 volts. I think the best device we've got now is probably just over 1, so we need to push that up a little bit higher to make it all work, because tandem devices, you've got to match, well, you've got to either match voltage or current or things like that. But yeah, it definitely, tandem devices definitely is a very promising direction for the field.
Where does your technology stand compared to Dysol and what they're playing around with? Second one, are you involved at all in printable battery technology, polymer batteries?
Yeah, so the VICOSC Consortium that I mentioned also has some activities in dye-sensitized solar cells, and that's the technology that Dysol work on. So that uses titanium particles that has dyes attached to it, and then some electrolyte that transports the charges. So it's a similar thin film technology, but just a slightly different architecture. We have had CSIRO and both Monash had some projects with Dysol on and off over the years. Dysol again have sort of changed their business model quite a few times over the years about what they're aiming to do, and but you know, they've made some very important discoveries and progress for the field in Australia. So again, it's not really a competition, it's something that's a little bit differentiated. Second question, yeah, CSIRO's got a large area of batteries research. Some of the people that actually, Noel Clark, who leads our printing work, who was in some of those videos, had previously worked on some printed batteries on paper and different substrates. We've got the group Adam Best, who is looking at different sorts of printed batteries for particularly military applications, so they don't have to carry all the batteries around. So in our display area, we've got some of their printed batteries, and you know, it makes a very good comparison to say, oh, well, you know, take this and the printed battery and put it together, and you've got a low-cost energy generation and storage device.
Okay, I think we're just about getting there. Thank you very much, Scott.
That's all right.
Thanks
for the questions. They were good questions.
It's great to come here and get some good news from time to time. Things can be a bit depressing, and here we find that Australia still is a clever country, and that there is some still government sponsorship of good work like this, which is good to hear. These discussion groups are a bit of a spin-off of VZE. VZE's main focus is on research into how we can transform Australia into a renewable high-tech economy, and that research costs money. Most of it is supported by individuals contributing perhaps monthly, and there's a form just outside the door if anyone would like to contribute in that way. Next month we have Dr. Matthew Rimmer from ANU, who will be talking about renewable energy innovation, patent landscapes, legal conflicts, intellectual property and greenwashing. And that will be on Monday the 7th of October at 6:30. And I thank you all for being here.